Okay, we are continuing the lecture for neural network training, and in this second part we will look at key concepts in the training process, backpropagation, and we will see how we will use the chain rule. Parameter update, we'll look at two examples, 1 point and more than 1 point, one data point and more than one data point, and the concept of convergence. Okay, so let's get going. Basically, we will use the backpropagation to compute. Let me get my pen here. Okay, we will use the backpropagation to compute the derivative of an internal variable. I'm sorry. So, say for example, we have this variable x, and we will see in the neural network training this will be a parameter or a bias that I need to update its value. To update the value, I need to compute the derivative of this parameter or bias. Let's just say we refer to this bias or weight as a variable x. The question that we need to answer is how we can compute df dx, which means I need to compute the change of function f with respect to the change in x. And this is this information is necessary for me to do the update for parameters, and the update for parameters will lead me to calculate the optimum values for parameters. Now, in this example, what I have is that I have, let's say, a t variable. It goes into an x function for this t, produces for me x, and then x goes into a z function and produces a z, and the z goes into an f function, okay, and produces an the final function here, or the final result. Example of z will be, for instance, let's say, for example, x squared plus x. Example of f will be z to the power 3 plus 3. And again, example of x will be, let's say, for example, t squared plus 5, for example. And now what I desire is to compute this df over df dx, which to say I want to know, to measure, to compute the change in f with respect to a change in x. That's exactly what I want to compute. Again, why? Because this is necessary to update the parameters, which is necessary to compute the optimum value for parameters. In this case, what I need to do is use the backpropagation, where in every stage I will compute the derivative for that variable in that stage and push it back. So that's why we go backpropagation. So it's easy for me here from f. I can compute df dz, and then to compute df dx, I can compute dz dx, which is from this equation. You can see this line here shows that it's easy to obtain. Then I need df dz. Why df dz? Well, it turned out df over dx, using the chain rule, I can compute it by multiplying df dz times dz dx. Now, I can get dz dx, right, the derivative of dz with respect to x, from the z equation. But where do I get df dz here, the derivative of the f function with respect to the z variable? Well, it has to be pushed back from an earlier stage, and then I can plug it in here. In this case, I will be able to compute the derivative of f with respect to derivative of with respect to x. And now I can push this value now back, because now if I need to compute, for example, df with respect to the t variable, that will be df with respect to x, which I computed already from here, multiplied with dx with respect to the variable t variable, which I can get from this equation right here. Okay, this process of pushing back the derivative results is what is referred to as backpropagation, and it uses fundamentally the chain rule, basically. Okay, so now that's what we'll be doing in the next slides. Okay, so let's take some numerical example here. Suppose I want to compute df with respect to x, df with respect to y, df with respect to z. I have a function here, f, in terms of these variables x, y, z, and the function is equal x plus y multiplied by z. In these in this slide and the coming few slides, we kind of use this data flow diagram, which is right here, to illustrate the concept and to prepare you for the notion of the nodes in the neural network. So we will replace this later on, this plus with a node in the neural network. Okay, so, but we go through this gradually. Now, obviously here this data flow shows that when you add x and y with x plus y here, we get a intermediate variable which is q. Okay, and this is used to apply the chain rule, and we will see shortly. And when we multiply this q with the z, we get the f function. So basically here, this is my q variable. Okay, now let's use some values here. X, assume it's -2, y equals 5, and z equals 4. If we evaluate this function, or we in the vocabulary of the neural network, we call this forward pass, okay, or forward propagation, inference. All of this refer to the fact that we are computing the function. We see we add x plus y, we get 3, multiplied by z minus 4, we get a value of -12. That is not what we are trying to illustrate here. Now, what we are trying to achieve here is to compute these derivatives. Okay. Now, if you see that to compute the derivative of f with respect to, let's say, z, it's the easiest. Okay, from this equation you can see. Oops, sorry. Oh, we flipped this too early. Okay. Okay. From this equation you can see this is equal x plus y. Okay, all right. So and now you can see that. Let's see if I get to my values here. For some reason my brain went blank. Okay, here which is equal to the value of q. Okay, so equals 3. I just derived this equation right here and I applied it right here. Now, in terms of deriving the delta f over delta x, we know that we have expressed f in terms of q, which is an intermediate variable, which is right here, and we know that we have we can derive q with respect to x. Okay, now delta f with q, we know that this is the equation here, and if I derive delta f over delta q, so delta f, sorry, well let's okay, so let's use another color here. See, so this is the equation. If I derive it, okay, delta f over delta q, I'm gonna get z. All right, so I got the first term. How about the second term? Well, here we have x plus y equals q, so I use this second equation here to derive this another intermediate variable, so delta q over delta x equals 1. And therefore now this equation right here, it will be equal to z. Okay, it will be equal to z. And now see if I have right. Okay, I'm not sure if I have those values plugged in. See in the next slide, do I have it plugged in? Yes, I have it plugged in. So here is the slide where I compute the delta x, delta f with respect to s, and we said at the end it was equal to z, and z equals -4, and this is exactly what I got here. Similarly, you can do the same math here. So this is delta f over delta q, which is equals to z, and delta q with respect to delta y, this is equals 1, again gives you -4, which is the value of z. We already computed the delta z here, and we said it is equal to delta f with the delta z equal to q, which is equals 3. Okay, so now so now you can see that we have achieved by going this way. We did this forward pass inference, and we are with going back here. Okay, all right, with going back, we have achieved the backpropagation calculation. Okay, I'm keeping here. Not happy with my pointer here, keeps changing things on me. Okay, all right, now so let's go to the next slide. So here is the backpropagation main idea as we illustrated. Going this way, this is the forward pass or forward propagation. Going back here, of course this is used to compute functions, right? And going back here is the backpropagation, and this is to compute the derivatives, okay, using the chain rule. More of the same point here, and we are going through all of this. The reason is, again, let's remind ourselves with the objective. We want to compute the change in loss function with respect to the change in parameters, because this is what we will use to update the parameters as we do the training, and this update process will lead us to compute the optimum value for parameters. It's important and critical to understand why we are doing this. Can't stress this anymore. This is why we are doing it. We are computing all these derivatives because at the end we will compute the change in the loss function with respect to the change in parameters, which are necessary for the update function to update those parameters, which is necessary to compute the optimum value for the parameters, right? Which is basically the main objective of the training process. Okay, so hopefully we linked these ideas in one logical series, so that we can understand what are we doing here. Okay, so operations in these nodes can in the data flow nodes can involve addition, multiplication, max operation, branching, and so the question is, so in this case you can see that z here is equal to a plus b. So what happened when I got a derivative for the loss function or any function with respect to z? How can I push it back here? Well, it turned out in the case of addition, you just pass on the same function. So when you back propagate, it will be delta L over delta Z. And again for the side where because here at some point you have a function here which produces A and a function here which produces B, so you want to back propagate, and in the case of the addition you back propagate the same value of the derivative. But what happens if we have a multiplication? Let's say for example Z equal A multiplied by B. In this case what we do when we back propagate the derivative, right, and the side of the A we multiply the derivative delta L over delta Z by B. And this is understood because when you try to do delta, let's say for example delta L over delta B, right, and this is equals what? Well, delta L over delta Z, right, multiplied by, let's see here, delta Z with delta B, right? But this was equals to what? Delta delta. Okay, I did the other side. Let's do this side. I'm sorry, I'm over delta A because I'm looking at this side here. So this is equals what? This is equals B times delta L over delta Z. So you can see here what we are doing. We're multiplying the derivative when we push it back to the side of A by B. Similarly, when we push the derivative to the side of the or propagate the derivative value in the side of the B, we multiply it by A. Again, why we are multiplying by A? Because delta L over delta, okay, I messed this thing up. This up here should be delta A over delta B, meaning the value of the derivative when we push it at this side here equals delta L over delta Z multiplied by delta Z over delta B. But this was equals to A multiplied by delta L over delta Z, and that's what we are seeing here. Okay? In case of max operation, we will use those quite frequently. In particular, for example, the ReLU. So if you have two numbers, you pick the max. Okay, so you have a derivative. Which way you back propagate it? So you propagate it only to the side which has the max value, and you propagate the value of the derivative. Okay, and there is the branch function where you add the derivatives. There are quite a few. Let's say if you will. Formulas or shortcuts that tells you what happens, but all in these notes, but all depends really on applying the chain rule. Whatever you have in terms of a function right here, okay, so here's a function, here's a function Z, and you have these data coming from these variables x, y, etc. So when you derive, when you want to push the derivative right back to the side of the x or to the side of the y, you apply the chain rule. Okay, it goes all back to the chain rule. Okay, let's take an example here. It's a little bit involved here, and in this example what we will do, here's a function here, okay, and this function, it implements it's the sigmoid function, but instead of one variable here, the x here is really more than it is multiple variables. So it's w0 x0 plus w1 x1 plus w2. So you can see it's an expression of multiple variables instead of x. So when we do that, we get this equation. Okay, oops. Okay, we get this equation, and what we need is to really we want to do forward pass to evaluate the function, and then back propagation to propagate the derivative all the way to the inputs. For the forward pass, it should be easy. These are the values of the w's, right, and the x's, And what we have is we just evaluate through these nodes. Again, these nodes are like data flow nodes. Observe, let me get my pointer here. I think the pointer will be better here, or highlighter, sorry. Oh, sorry. There's a pointer I meant. Okay, notice that here, in this expression here, okay, what we will do, we are creating here an intermediate variables. So for example, we created intermediate variable of z6, which is equal w0 x0, which is right here. This is z6, and an intermediate variable z7, which is w1 x1, which is right here. This is z7. You can see w1 x1 multiply, the result is in z7. And plus w2, we create z5, and you can see here is z5. Okay, oops. So z5 is the addition of z6 and z7, which is basically w0 multiplied by x0 plus w1 multiplied by x1. And when you add w2, you get z4. So you can see this, all this here. This is the z4 variable, right? Now, if you negate z4, you get z3. So the whole thing here is z3, a negative plus this expression. Now, if you raise the z3 to exponent to e, then you get z2. So you can see here z2 is, we raise the result of z3 to e, to the power of e. Then if you add plus 1, we get z2. So plus 1, we get here z2. So there is a typo here. I need to fix it. So this is a z1. This is z1 here. Okay. All right. Now, so I'm assuming have these values for the w's. Okay. So w0, the initial values are in green, or let's just say the forward pass, the results are in green. The back propagation, the results are in red. So initially, the w0 equals 2, x0 equals minus 1, w1 minus 3, x1 equals minus 2, w2 equals minus 3. Then I perform the operation. I multiply w0 x0, and I get here z6 minus 2. So here is, let's see if I can multiply 2 times minus 1. I get minus 2 for z6. Okay. Now w1 multiplied by x1. Minus 3 times minus 2, I get 6, which is z7. I add z6 and z7, I get z5 here, which is 4. Minus 2 plus 6, I get 4. Then when I add to z5 this w2, minus 3 plus 4, I get 1, which is the value of z4. Negating z4, 1 multiplied by minus 1, I get minus 1. This is z3. Raising z3 to the power of e, it gives me z2, which is 0.37. Add to 0.371, I get 1.37, which is z1. And inverse 1.37, 1 over 1.37, I get 0.73, which is the value of the function. So the forward pass now gave me the value of 0.73, sorry. Now, my next job is to back propagate the derivative. So let's just assume that delta f equals 1. And I can assume it's 100, it's 1,000. I'm just starting with a value of 1. So if it is coming from another function or another module, I will have to put the results that is being propagated from the other module here. But I'm just going to assume that df equals 1. Now, the question is now, as I propagate backward here, okay, I need to start calculating df over dz1, df over dz2, df over dz3, sorry, this is the one, df over dz4, etc., etc. And I'm going to use the chain rule. So let's see here. If I change this one to a pen with red here, I believe red is good. So I need here to backpropagate and calculate df dz1. Notice, it's important to notice that I cannot calculate the derivatives at the end unless I calculate the derivatives at the beginning, because backpropagation starts from the output all the way to the inputs. So the very first one I need to calculate is df over dz, delta f over delta z1. Well, delta f over delta z1, I know that the f can be expressed 1 over z1, so I can compute the derivative as minus 1 over z1 square. Okay, this is the derivative right here. Okay, this is the derivative minus 1. Now, since I have already computed z1 as 1.37, I can plug in the 1.37 right here, and I can get this value of the derivative of minus 0.53. And I record this number right here. So what I did right now, I computed delta f over delta z1. Now I can propagate this back to compute what? To compute delta f over delta z2. So now I need to apply the chain rule. Delta f over delta z2 equals delta f over z1 multiplied by delta z1 over z2. Well, delta f over z1, I have already computed it. It is right here. Okay, but what is delta z over delta z2? Well, here is the relationship between z1 and z2. It turned out delta z1 over delta z2 equals 1, and therefore delta f over delta z2 equals the same as delta f over delta z1, which is minus 0.53. So I take the value here and I record it right here. Watch how I am propagating back. Okay, therefore the name backpropagation. Now I need to compute delta f over delta z3. Well, delta f over delta z3 consists of computing delta f over delta z2, which I already computed, multiplied by delta z2 over delta z3. Well, here's the function that tells me the value of z2 in terms of z3. I derive it, and I get the e to the power z3, right? And then I plug in the number of z3, which is let's see, which is right here. Okay, right, which is right here. So now I multiply this with minus 5.3. Now notice that e to the power z3, the z3 value is minus 1. So I plug in minus 1 here, that comes to 0.37, multiplied by minus 0.35, and that comes to minus 0.2. So I record the minus 0.2 right here. So this is the value of delta f over delta z3. Okay? Now, I need to backpropagate to compute delta f with respect to z4. Okay, and that is equal delta f over delta z3, which I already computed, multiplied by delta z over delta z4. And here is the equation that will give me the delta z over delta z4, okay, which is minus 1. So I multiply minus 1 times minus 0.2, and that gives me 0.2. Now minus 0.2 because the minus 0.2 is the value of the delta f over delta z3. And therefore delta f over delta z4 equals 0.2, and I come over here and I record it. Now let's push back now, go back propagate and compute delta f over delta z4. I should say here there is a delta, okay, delta z5, sorry. There is a d here which is missing. Okay, now so this is equal delta f over delta z4, which I already computed, okay, from here, okay. times delta z4 over delta z5, right? Which is I can get it from this equation right here. Okay, I can get it from this equation, and clearly this is equals to 1 if you derive this delta z4 with respect to delta z5 from based on this equation should be 1, and this is where I plugged in the 1. Delta f over delta z4, I have already computed it, 0.2, so the result is 0.2, and therefore I have a delta f over delta z5 equals 0.2. Now back propagate. You can see this is a continuous process of back propagation. Now I can compute delta f over delta z6, which is equal to delta f over delta z5, which I already computed. It's right here. Multiply by delta 5 over delta z6. Again, I forgot the delta here. There is a delta here. Okay, this I can compute it from the equation. Turned out to be 1, so I multiply 0.2 times 1, I get 0.2, which is right here. Similarly, I can compute delta f over delta z, and this is equal to 0.2 times 1, and then this is the value right here. Okay, now delta f over delta dw2 equals delta f divided by with respect to z4 multiplied by delta z4 with w. I have already computed delta f with respect to dz, which is right here, 0.2 equals to 0.2. Okay, so this is 0.2, and this one I can derive it from this equation, which is 1, and that comes to a result of 0.2, and therefore you can see we have recorded a 0.2 right here. Now let's see if I want to compute delta f over delta w0, and this is equal delta f over delta dz6 multiplied by delta z6 divided by dw0. Now I have already computed the dz6, which is right here. Okay, so I can take this and plug it 0.2 here, and this is I can derive delta z6 with respect to dw, and this comes to be x0, right? And now I multiply minus 0.2 times the value of x0, which is minus 1, and that comes to let's see, I'm sorry, 0.2 times 0.2, this should be 0.2 times 0.2, it's not minus, multiplied by minus 1, that comes to be a minus 0.2. Okay, and similarly I can compute delta f over delta x0, which is 0.2 times the value of w2, and w2 is equal to 2. This is the value right here, okay, in green. So 0.2 times 2, that comes to 0.4, which is right here. Similarly, I can compute delta f with delta w1 and delta f with delta x1. And you can see how, again, the idea this to illustrate how we can go backward and propagate. Now this is, we know that this entire thing is the sigmoid function, so I can recompute this whole thing but save myself a lot of intermediate computation. All right, and I can use the derivative of the sigmoid function. So you call all these details now, I can hide them, whatever details I had before, I can abstract them with the sigmoid function. And the derivative of the sigmoid function is 1 minus sigmoid times sigmoid. And the input data for the sigmoid, which is the z4, is 1. The output of the sigmoid is the f, which is 0.73. So when I push back here, right, so this will be the derivative of the function with the derivative of z4, which is right at this point here. It is equal the sigmoid with the value of 1. Where is the value of 1? It's right here. This is the input right here. times 1 minus sigmoid evaluated at point 1.0. You do the math and you get 0.2, which is right here in red. Now, using the sigmoid function instead of these internal computation saves me some time, right? But whether you use the sigmoid or you use the detailed calculation, you should get the same results. Okay. Now this is here some derivative of some functions here, the ReLU, the sigmoid, as we have seen it just a second ago, and some other function. This is the leaky ReLU, okay, and basically the leaky ReLU here looks like so here is here, and then in the negative is the slope is small, so you basically have two slopes here. Okay, so you have for x greater than 0, the derivative will be 1, and for x less than 0, the derivative will be alpha, which is the small smaller than 1. Typically alpha is less than 1. Okay. All right. So now we will look at a neural network example here to do backpropagation. So far we have done backpropagation on numerical examples just to illustrate the idea. Now let's apply backpropagation and the chain rule on a real network, neural network example. And in this example, what I have here is that I have a single input x here. Okay, let's take x here, and a single output here, and I have two nodes, right? And I have these weights, W1, okay, and a bias for this node, and oops, and let me just try to hold this right way, okay, and a weight W2 and a bias for this node. The result of node 1 and node 2 multiplied by W3 and W4, and they are summed to find the final value, which is the function right here. Of course, you can see easily my parameters that I'm trying to optimize: W1, W2, W3, W4, and B1, bias 1 and bias 2. And the functions here are the ReLUs. Those are the activation functions inside the nodes. Okay. And then I have these intermediate variable. When I multiply the input with the weight plus the bias inside this, I'll refer this variable as V1. Once you apply V1 to the ReLU function, the output is Z1. Similarly, the other node, V2, is the multiplication of the input with the weight, right, plus the bias, right? You apply V2 to the ReLU, you get Z2. Okay, those intermediate variables will help me through the calculations. Now, recall that we use the variable k to indicate number of input training patterns. In this case, we will look at two cases where we have just one training pattern and two training patterns, just to go gradually in the complexity of the problem. Okay, so here what I want in this example, I'm going to assume these initial values, okay, for my parameters. I am going to assume that when I have a 0.1 input, the expected output should be 0. Okay, so that's basically my training data. Okay, I'm going to assume learning rate to be 0.5, and so learning rate times 2 over 2k, and this k equals 1 because I have one input pattern. Okay. It is equals to 1. This is to show you that I'm going for now to put aside this 2 over k plus learning rate, so we can derive the intermediate expressions in an easy way. Okay. So now let's do the inference, which is the forward pass. All right. Okay. So let's go over this one more time. Okay. We've done it in the previous lecture. So here's your input. you multiply it by the weight, you add the bias, okay, and you get the variable V1, which is equals to 2. So you apply V1 into ReLU, you get Z1 equals 2. You multiply Z1 by this weight, this is -6 here, so this is -6 here. And similarly on the other side, you take the input, you multiply it by W2 and you add the bias, you get this should be V2 right here. This should be V2. And V2 equals 0.8. And here we apply this V2 to the ReLU, you get 0.8, you multiply it by the weight and you get 0.8. Let's see if I get this correctly. Okay, 0.8. So this one here, sorry, this was 0.4 here, and plus 0.8, and I will get -4 plus 0.8 minus 3.2, which is the value of the function. Okay, now what we will do is now I did the inference. Okay, I need to do the back propagation. And the back propagation here, we will demonstrate the back propagation using the chain rule and driving all these delta L over delta parameters using the chain rule. And then what we'll do, another method, is using the back propagation, and only we propagate the results, no expression. Results are and this is basically the practical way. In other words, we'll show how you can propagate the results as opposed to going through the derivative and applying the chain rule. Both methods are correct, but the second method is more practical and more friendly for computations and algorithms and programming. I'm going to stop here and we'll continue this discussion in a different part, because for the interest of time and having a reasonable length of the lecture. Thank you.